normally it is abbreviated as AGC, automatic generation controls. Okay, so in last previous class, we have learned about the speed governor, right? There are two types which we can control the frequency. First is by primary control, that under primary control it is a speed governor, and then another one is a secondary control. So secondary control will be automatic generation control. Okay, so and then so automatic generation control, if I'm not mistaken, you might have learned, or if you have not learned, then you will learn in power electronics application. I think you will learn in power electronics application also, but for this here we'll not learn in detail about the AGC, but here we will learn about the application part of AGC. Whereas in power electronics application, or you might have learned in power electronics, if you have not learned, then you will learn in power electronics applications. So in that you will learn detail about the construction of AGC, but here we will not learn the constructional detail, but instead we'll use this AGC in the control of frequency. Okay, so how we will control the frequency by using a AGC? It is a secondary uh, control. Okay, so primary control is a speed governor. Okay, so these are some basic fundamentals of automatic generation control, which you can go through. And here in this slide, just I have made the differences between primary control action, that is speed governor, and then secondary control action, that is under automatic generation controls. Okay, so you can just read this slide so you will understand that. But very important thing is this: there are two objectives of AGC. First, main or a primary objectives of this AGC is to regulate the frequency to the specified nominal value. So example, so our specified nominal value may be 50 hertz in Asian countries, and in some other countries it is 60 hertz. But in a system you may get around 60, example 49 hertz or 50.5 hertz or 51 hertz, which is not a nominal value, right? So if you employ this AGC concept, then this AGC concept will bring back this frequency to the nominal, specified nominal value. And also, okay, so to maintain the interchange power between control areas at the scheduled values by adjusting the output of selected generators. So these are the primary objectives of AGC, automatic generation control. First is to regulate frequency to the specific nominal value, and then another one is to maintain the interchange of power between control areas, which means, so here control area means normally this AGC will not employed in all generating units, will employ only at the selected generators. Okay, so then there will be two control areas. So example I will give it there. Chuka as a one unit, the overall unit. I'm not talking about the individual unit. Okay, so we'll consider Chuka as an overall unit, which will generate 336 megawatt, and then Tala another unit. So which means Chuka will become one control area, Tala will become another control area, and we will connect this to a grid. So which means it is interconnected. Okay, so in such case, so what we will do is we will employ a automatic generation control at the Chuka and then some to the Tala. And if there's some changes in load in the Tala, so it will affect the Chuka also. But if you have a automatic control generation control, so it will be bring back this frequency to the nominal value. How, we'll see on later on. Okay, so this is a first primary objectives. And then this type function is commonly we call it as a load frequency control, LFC. And then another objective is a secondary objective of automatic generation control is to distribute the required change in generation among units to minimize operating costs. Okay, so which means Chuka has a 4 unit. So from 4 unit, we will not install or employ automatic generation control in all 4 units. So we will just employ in 1 or 2 unit, which means this distribute the required change, which this 1 unit can be allocated as a one which will respond to the change in load. Okay, so that will minimize the operating cost. Means, so if you employ all, there will be a huge operating cost. So now one generator can be specified so that we can uh, employ the automatic generation control. Okay, so this is a secondary objective. So basically there are two objectives. First is primary. So under primary, there are two. One is to regulate frequency to the specific nominal value, and then maintain the interchange power between control areas. Example I have given. And then another objective, which is a secondary objective, is to distribute the required change in generation among units to minimize the operating costs. Okay. And then, so now first we will see this AGC in the isolated power system. So everybody knows that what is isolated power system. This isolated power system means the power system which is not connected to the grid. Okay, so everybody knows that isolated power system. So now in isolated power system, there is no issue of interchange of power, right? Because only one power station, right? It has been not connected to grid, which means there is no requirement of interchange of power between the one generating station to another generating station, because in isolated power system it will be supplied by power will be supplied by one generating unit only, so the generate unit only. So that's why, so the interchange of power is not an issue, which means primary objective. Under primary objective there are two objectives. So maintenance of interchange of power is not an issue in isolated system if we employ. So which means we are not required to take care of interchange of power. But in isolated system, only function this AGC will perform is restore the frequency to the specified nominal value. So which means if you employ this AGC, so it will restore frequency to the specific nominal value. If it is a 50 hertz, so example in Bhutan it is a 50 hertz. So now if you employ this in an isolated power system, then if there is frequency deviation from 50 hertz to 49 hertz or 51 hertz, if you employ this AGC, then it will restore the frequency to the 50 hertz, which is a nominal value. Okay, then this how it will be done is, okay, so in isolated power system it will be accomplished by adding. Okay, so before that, so I will explain with this diagram. Okay, so first you see at this diagram this part where I have circled. Okay, so first if you see this one, so you can see that this is just normal one which we have learned earlier yesterday's lecture. There is a units on primary speed control only, which means it employ only the speed governor. Okay, so this how it works, you know that. And then let's assume that in this isolated power system there are two generating unit. Okay, so example, so let's in Bhutan let's take it at Dagachu. Dagachu there are two units. Okay, so then one unit is just employ the primary speed control only, which means speed governor. And then second unit, let's assume that, so we will choose to install or employ the AGC. So there, what we can do is, okay, so other thing will remain same till here. It is same as unit 1. Okay, under primary speed control only, it remains same. Only difference you can see is, since we are employing the automatic generation control, so which is known as a supplementary control. So we have selected this unit to employ the AGC. So AGC, just we will add this. Okay, in the load reference point, before load reference point, we will add one integral control action, or we call it as adding reset. This is also known as a reset or integral control, which acts on this load reference point. Okay, as shown here. Okay, so I have shown here. But what this integral action will do is it will ensure that there is zero frequency error. Okay, zero frequency error in steady state. So when it reaches to steady state, so there will be a zero frequency error. Okay, so this is additional. So that's why we call it as a AGC or a supplementary control. We have selected this one. And then if there is some deviation, so first what it will do is this will perform first. Okay, so first this speed governor will perform its function when there is a, let's say there is some speed deviation, okay, so which you can measure from here, and then you will get some actuating signal, and then governor will function that one. Okay, so that, and then it will have an actuating signal here, and then turbine will adjust this, and then we'll get the required speed. But when you employ this AGC, what it will happen is here in steady state, when it reaches to steady state, we never know that frequency may not come back to 50 hertz. It may remain in the 49 hertz or 49.5 hertz. Okay, so normally you might have seen in the powerhouse. So your frequency will be either 49.5 hertz, and then that operator will say it is okay. But if you want to have a good quality power, then we require the nominal value, right? It's specified. So now what we can do is we can employ this one, and then this interval will make zero as, okay, ensure that zero frequency error, so which means there's no error at all. So whatever frequency is there, so you will get that frequency. Okay, but here in speed governor only we will try to adjust, and then it will keep within the range, which is within the acceptable range. Acceptable range may be 49 to 51 hertz, but nominal value may be 50 hertz. So if you employ AGC, then so you will get a exactly 50 hertz nominal frequency. Okay, so then one drawback, okay, of the AGC is, okay, so it will perform, okay, so the supplementary generation control action is much slower than the primary speed control, which means first primary speed control action will be performed, that is speed governor, and then only so this secondary generation control, or we call it as a supplementary generation control action, will perform. Okay, so in such case what it does is, as it performs slower, it takes effect after the primary speed control, which we normally we know that primary speed control are which will act on all the units on regulation, right? So which means all unit it has been given connected with the primary speed control, whereas this supplementary generation control is connected, or secondary generation control or AGC is employed only to the selected units. Okay, so it will perform there, and then it will perform, okay, so effect after the primary speed control has stabilized the system frequency, which means system frequency here it might be acceptable range 49 to 50 hertz. Okay, so this primary action control will stabilize the system frequency, but the after stabilizing that only this supplementary generation control, that AGC will effect of AGC will be there. Okay, so which means this AGC will adjust the load reference setting of the selected unit. Just it will perform for the selected unit and their output power. Okay, so based on that selected load reference setting of selected unit, then their output power, and to override the effect of composite frequency regulation characteristic of the power system, which means so it will override the frequency, okay, regulation characteristic of power system. And in doing so, so what it will do is, so it will restore the generation of all other units, even not on the AGC, to the scheduled values, which means so where it will perform in the one selected unit at the meantime when it so so other generating units will also, okay, restore its to the scheduled values, which means so just now we are talking about the frequency, so it will be 50 hertz. Okay, so then this is about the isolated power system. But nowadays, so isolated power system is becoming obsolete. Even power generation from renewable energy like wind and solar is connected to grid. Okay, so mostly isolated power might be having just one or two solar panel in the roof and then just generating from there only. So now in modern days, so what we will do is we have to concern about the interconnected power system, which means so power from the Chuka, power from the Kurichu, power from the Tala, power from the Pasachu or Dagachu, and now Mangdichu, all it has been connected to the grid. So in such case, how to employ the AGC, which means automatic generation control. Okay, so in such case, so now first let's consider as okay basis for supply. Let's consider a two-area system. So here in such case we will consider as two-area system, area 1 and area 2. So we'll not go for all. Okay, so now example, let's take it area 1 to be a Chuka hydropower plant, area 2 to be the Tala hydropower plant. Okay, so now to form the basis for supplementary control of interconnected power system. So first, okay, let us look at the performance of a primary speed control only. Okay, so before we employ that AGC for frequency control, so first let's see how this primary speed control, which means speed governor will perform. So after you get clear about that, then only we'll employ the AGC and how it performs. So, but for that one, let's consider two area system shown in figure 2. Okay, so that two area system. So first area 1. So let's assume area 1 to be Chuka here. Okay, so then here let's say it to be Tala. Okay, area 1 and area 2, and then it has been connected. This area 1 and 2 is connected by a tie line, and then that tie line reactance, let's assume that XTIE. Okay, so and then here in this symbol, arrow sign has been shown to us the area 2, which means power flow from area 1 to 2. So area 1 we have assumed Chuka. So now let's assume that power flow from Chuka to Tala. Okay, so now what is tie line? So you might be knowing. Okay, so transmission line. Okay, so this tie line, everybody knows what is tie line. So but tie line, it is a transmission line of a area connected to its neighboring area is known as a tie line. Okay, so now for a low frequency studies, so now what we have to do is with this two area system, just using this block diagram, we will not be able to understand anything. Okay, so just here we can say that power is transmitting from area 1 to 2, but so let's modify this two area system or represent it by a electrical equivalent circuit. Okay, so for low frequency studies, such area might be represented by okay, so electrical equivalent circuit. Okay, so which means equivalent generating unit exhibiting overall performance means generating here. It means this is a generator electrical equivalent circuit. So and then this area generator 1 will have some reactance X1. Then this is a generator 2 which will have a reactance 2, and then this is a reactance of a tie line. So total reactance will come as XT. Okay, so such composite model. Okay, so in such case, when we convert to electrical equivalent circuit, what we are doing is we are not considering any inter-machine oscillation within each unit, which means in area 1, we are not considering any oscillation effect. Okay, machine oscillation in this area or this area. Just we are drawing one equivalent circuit because it is acceptable. Okay, so in such case. Okay, so now what we can do is using this basic. Okay, so we using this basic electrical equivalent circuit. So now we will derive and then see how this speed primary speed control function. Okay, so now this figure 3 I have already explained. So then we know that this power flow on the tie line from area 1 to area 2 is given by this equation number 1, and then this equation number 1, you know, this is from the swing equation, right? So which will be equal to E1, this is a voltage at generator 1, then E2 is a voltage at the generator 2, and XT is a total reactance, including reactance of generator 1 and 2, and then tie line. and this is a angle, right? Sine del 1 minus del 2. Okay, so now this is a basic equation which we will get, which we have learned and then we got from this swing equation. Okay, so now what we have to do is this equation 1, we have to linearize about an initial operating point, which will be represented by initial operating point del 1 equal to del 1 0, and then del 2 will be equal to del 2 0. Okay, initial condition we are talking about the initial. So now if you linearize this one, so what we will get is, so we will get that change in power del P1 2. So we have considered power flow from area 1 to 2 will be given by T del 1 2. Okay, so what is mean by del P12? It is a changes in power flow from area 1 to 2. So area 1, so example we have considered is Chuka now, and then area 2 is Tala. So power flow from Chuka to Tala we have considered, and then if you linearize this one, so we'll get represented by this equation number 2. So where this del 1 2 will be equal to del 1 minus del 2, because power is flowing from the area 1 to area 2, which means area 1 is at the higher potential than the area 2. And what is T? T is a synchronizing torque coefficient. It's also got from this basic swing equation only, which will be given by T is equal to E1 E2 by XT cos del 1 0 minus del 2 0. So why we have reflected by del 1 0 and del 2 0 is because we have linearized the equation number 1. Okay, so this is a basic equation, okay, for two area system. So now that is electrical equivalent circuit which we have drawn. Now we will explain from the terms of block diagram. Okay, so now let's say area 1. Okay, area 1, this is the area 1. Okay, okay, this will be area 1, and then another one is a area 2. Okay, so this is a area 2. Okay, so still now we are talking about without employing AGC. Okay, so first we have to get the clear concept of without employing AGC or only a primary speed control. So now see here. So in this one, block diagram representation of system is shown by this figure 4. Okay, with only primary by equivalent inertia constant M. So M1 is for area 1, M2 is for area 2. Okay, and velocity constant D1 for area 1 and D2 for area 2, and then this R for speed group characteristic, which we have learned in the earlier session. Okay, so now here tie line will be represented by, okay, so this tie line will be represented by synchronizing torque coefficient T. Okay, so now let's assume that, so there is a positive, okay, so positive del P12. So what it mean by, if there is positive value of del P12, what it mean by this? Okay, so a positive del P12, it represents the power transfer from area 1 to area 2. Okay, which means, okay, so increasing the load of area 1 and decreasing the area of load 2. So that's why you will see that feedback at the, okay, feedback at the area 1 is negative, and then feedback at the area 2 is positive, which means this is a positive value, power flow from area 1 to area 2, which means for area 1 there is a increasing load, and in area 2 decreasing load. Okay, so and then it will be represented by, okay, so by feedback system. So here feedback negative for area 1, positive for area 2. Okay, so these are the basic. Okay, this all other one, this portion we have learned in the earlier session, means yesterday we have learned about these two all. Okay, so now only thing is additional thing we have to learn is when it is interconnected, these two by a tie line. Okay, so yesterday we have just learned about this one area only. So now with this, so now we have to derive a mathematical equation involving frequency, because we are studying on the frequency control. Okay, so now basically what you will get is, okay, steady state. So we are, okay, so assuming that after some time it reached to the steady state, and then what is the value frequency of the steady state frequency we'll try to find out. So now steady state frequency deviations, normally it will be given by uh, del f, which will be equal to f minus f naught. So when it reaches to steady state, it means that frequency deviation will be remain same for the two areas, that is area 1 and area 2. And if there is any load change, okay, so total load change in the system, okay, so by del PL, then this, it can be represented by frequency change can be represented by equation 4. Okay, so equation 4. So how we got this equation 4? So let's derive and then see that del f will be equal to del omega 1 equal to del omega 2 equal to minus del PL by 1 by R1 plus 1 by R2 plus D1 plus D2. How we have got it? This actually it says that in a steady state frequency deviation, okay, deviation, that is f minus f naught, which will be equal to del f, is same for two machine. Okay, so then if load changes, okay, total load in the system changes by del PL, then frequency in the system can be represented by, okay, represented by this equation number 4. So how? So let's see. Okay, so now let's consider the steady state value following an increase in area 1 load by del P1. Okay, so now what we can do is, so for two area system only, so what we can do is consider a steady state values following an increase in load area 1 load by del P1. So now if we increase this one, so now when we see back the block diagram, so for area 1, okay, so for area 1, so what we will get is excuse me, so my system is not working perfectly, so it takes some time. Okay, so see here, so now for area 1 in the steady state, so now what you can see is, for area 1, you see that for here you can see that there is changes in load del PL1, and then mechanical power is there. Then from here we have a changes in load in the system. Okay, so del P1, sorry, not in the system, that's power flow from load area 1 to area 2, del P1 2, and then this del PL1 is a changes load in this area 1, and then del PM L, so not L, it is a 1, is a mechanical power T block. So now see here, for area 1, we get that del M1, so del M1 is positive here, right? 1 is minus del PL1 minus del P12. So this is how we have got it. L1 or del P12 will be, it should be equal to the changes in the frequency, okay, or deviation of frequency times the damping constant d1. Okay, so this is a changes in the frequency change. Okay, so equation number 5. Then similarly for area 2, you can see here area 2. So all are positive except minus del P L2. Okay, so then you will get that del PM2 plus del P12, okay, 1 2 is equal to, okay, so it will be equal to del F D2. So here will not reflect that del PL1 because we have considered that load changes in the system 1 only, which means there is a frequency power flow from area 1 to the area 2. So which means that's why we have not reflected del PL2. Okay, so this is equation number 2. So we are deriving this from the block diagram to get the changes in frequency deviation in steady state. So now what you can do is, so you have learned in the earlier class that change in mechanical power depend on its regulation. So del P, so del PM1 will be equal to minus del F by R1. Okay, del PM2 will be equal to minus del F by R2. This one we have learned in the yesterday session. Okay, so which we have done that del P1 by del P2 is equal to R2 by R1, like this we have learned. So this is a basic equation which we have known that mechanical power depend on regulation. So then substituting this equation 7 in equation 5 here. Okay, so you substitute here, so you will get del F equal del F into 1 by R1 plus D1 will be equal to minus del F, del P12 minus del PL. So let it be equation number 9. Similarly, you substitute equation 8, this equation 8 in equation number 6 here. So when you substitute there, so you will get this equation number 10. Okay, so you try to do in a rough paper when you revise that, you take out that and then substitute this equation number 7 del PM1 equal here, or you can do in any other mathematical expression and then you try to substitute by del F or del PM1 or whatever it may be, you try to substitute, so you'll definitely get this equation 9, 9, 10. Okay, so after that what you can do is solving equation 9 and 10. So this equation 9 and 10 here, so directly you can solve that del P12 is equal to del F 1 by R2 plus D2. You can substitute here, just minus that, you take to right hand side and then you will get this basic equation, so which will be equal to del F equal to minus del PL1 divided by 1 by R1 plus D1 plus 1 by R2 plus D2, which will be equal to minus del PL1 by beta 1 beta 2. We have considered that where beta 1 and beta 2 are the composite frequency response characteristics of area 1 and area 2 respectively, which means this is a composite frequency response characteristic of area 1 and then area 2. So just for simplification, we have just represented it by beta 1 and beta 2. Beta 2. So if you keep this much also, it's fine. So this is how we got the equation. Earlier I said that, see here, steady state frequency deviation is the same for 2, and then for total load change of del P, so we'll get change in frequency will be given by minus del PL by this equation, right? Okay. So this is how we will get this. This one you will get it. Just rearrange there, and then you will get this equation. This is how we have got this equation. And then similarly, what you can do is del P12. Okay, so you can get that del P12. Substitute this. Okay, so del P12 and then you substitute that del F, so you can get all this power, how much power has been transferred from area 1 to area 2 you will get by equation number 2. Okay, so are you getting now? So del P12 is a power transfer from area 1 to area 2. How much power you have transferred, you know that. And then what is the frequency changes by changing a total load of del P will be given by this one. Okay, so are you getting now? So this all equation can be represented or depicted in figure 5, which means effect of change in area 1 load. So if there is changes in load in area 1, what will happen to the area 2? So normally, if I have not mistaken, okay, so one of the RCC question I have seen this type of question they have asked. Just they have made an assumption that if there is sudden change in load in Chuka, and what will happen to the area 2, we have assumed that is Tala. Somehow like this, I'm not remembering exactly exact question, but I have seen one question they have asked like this. So if load changes in Chuka or generating area 1, what will happen to the generating 2? So all this can be represented like this, and then we can explain here. Okay, we're using this symbol block diagram. You can explain, and then so definitely some of you will perform good in RCSU. Okay, so that's why I feel that you can perform better than other electrical engineering graduate, because this we have not learned in any undergrad level. Okay, so we have learned even in a master level, only few of our friends have learned about this concept. Okay, so but definitely some of them are asking in the RCC, so you please take note of it. So now what it says is, now just now we'll only talk about the area 1 only. So if there is load changes in area 1, so now let's assume that increase in load area 1 load by del P1. So initially we have this all. Okay, so now but there is a sudden increase in load del P L1. Okay, so what will happen to other system? Okay, which means this will result in frequency reduction. If there is a sudden increase in load, so definitely there will be a frequency reduction in both the areas. Okay, so area 1 as well as area 2, because it is interconnected by tie line. Okay, so result in frequency reduction in both areas, and a tie line flow of power del P1 2 will also be reduced. Okay, so if there is increase in load in area 1, what it happen is del by a del PL1, then it will result in frequency reduction in this area 1 as well as area 2, and tie line flow of del P1 2, which is flowing from area 1 to 2, will also reduce. Okay, so now another case, let's see. If negative is there, if sign is negative, it means that power will flow from area 2 to area 1. Just for your understanding purpose, I'm saying this. So now this tie line can be represented by this contribution of regulation characteristic and then. Okay, so now what it happened is, so now in your answer, if it asks somehow like this in the RCC, then you can say that if there is a changes in load in area 1, so here we have considered as CHP. So now what is the effect on area 2 if they ask? So it means that, so frequency at area 1 as well as frequency at area 2 will reduce if it increase the load. Okay, but another one is a vice versa, reduce. Then what it will happen is, another effect is power flow in this tie line will also decrease. Okay, so if you write this much, then it is more than enough. Okay, as per the question. Okay, so I still remember in one of I don't know year, I'm not remembering, but so 1 year they have asked question related to this one. Okay, so then the effect is, we can say that when load increase in area 1, so frequency for area 1 as well as area 2 will reduce. At the same time, power flow from tie line will also reduce. Okay, so this is the effect. But now if it considers same way, if we found out to be, so if you have some mathematical calculation, so which I will give on later on example, if you are required to find, okay, using all this data, and if you find that power to be negative, P1 to be negative, it means that power is flowing from area 2 to 1. So which means we can write that del P1 2 will be, okay, we can write as del, so negative del P12 can be written as del P21. It means from area 2 to area 1 power flows. Okay, so this is a basic concept about the, okay, so this is a basic concept what happened to the frequency and then power in area 2 if there's changes in area 1. Okay, are you able to get it? Okay, so
yes,
similarly now we can go for a change in area 2 load by del L2. So we can get this equation. You can just derive that, and the all equation we have got it. So instead of that, so we'll get just change this one, and then del 1 2 will be equal to minus del P21 will be given by this relationship. Okay, so these are the two equations for load 2 if there is changes in load 2. So now this above relationship is a basis, or it forms the relationship basis for the load frequency control of interconnected system. So now how to control will depend upon this value beta 1 and beta 2, and del how much power changes are there. So they based on that, so this change in frequency we can find it. Then based on that we can find del 1 to how much power. Okay, so this will form the basis for the load frequency control. Okay, so now, so today, so I have planned to stop here or here. So now if you have any doubt, okay, so if you have any doubt, you can ask them. Okay, any doubt? Okay, any doubt?
No, sir.
Because today I've kept this much only, so it's at least if I take more,
Thank you,
less
sir.
than less than 1 hour, so your data may be safe for some other useful purpose, right? So that's why I will not take much longer time. Maximum I will teach around 2 to maximum I will take around 30 to 35 minutes, at the max 40, I feel 40 minutes, and then I thought I will stop here. Okay, so now
Thank you, sir.
if you have any doubt, okay, so don't hesitate, you ask, or if you're not having doubt now, when you revise this, you may find some difficulty, so that time you can email me or write in the VLE also, it's fine. And then one thing is, so definitely in this Friday there is a review meeting among the dean and then heads. So that time I think teaching style may change or it may continue with this one. So never know. So after that, so I will inform you. Okay, so that's all for today. And then so I have said this is asked in the RCC. Okay, so please remember that when load changes in area 1, what is the effect on area 2? Okay, example I have given. So in RCC, they are not asking in terms of area 1 and area 2. They ask in terms of Chuka or Tala or Basachu. But if there is a load change in Chuka, what is the effect in Tala? If it is a grid connected, they will ask definitely. Okay, some may ask. So that time you said that if load increase in Chuka, example. Okay, so if load increase in Chuka, so frequency at the Chuka definitely it will decrease, but effect at the Tala will be, it will also decrease the frequency. So just now, don't talk about the voltage. Voltage is in unit 3. Okay, so in unit 3, we'll see what will be the effect of voltage. But just now you have to know that frequency at the Chuka as well as Tala will also be decreased. And at the same time, power flow from the tie line will also reduce or decrease. So now how to go about this? Okay, so this is how we can control the speed. Okay, so now just for before leaving you all, so just as a attendance. Okay, so today Rajesh is there, Karmong is there, Kencho is there, Namit is there, Nimsring, Punab is there, Roshan, Samjana, and Sonam, then Jamso, Ugin Wangchu. Okay, other Ugin Punso, and then the rest. Kilo Wangchu is absent, right? I think he is permanently absent, even he is not signing in the VLE, right? Okay, so that's all from my side. And if you have any doubt, so please don't hesitate. You can either mail me or write in the VLE, or so this derivation part. So just I have said it will be, you will get like this equation 5, 6 like this, but you can practice by in a rough paper. So definitely you will get it. So if you are not getting that, so you can inform me. So I will write by hand and I will scan and then submit to you all. Okay, sir. Okay, so
Okay,
thank you.
sir.
Thank you for coming online.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.